Before we begin looking at hemostasis, I wanted to go over the general anatomy of a blood vessel. There are three layers in the wall of the blood vessel. We call these layers tunics. Tunica intima is the innermost layer, and it lines the lumen of the blood vessel. It consists of simple squamous epithelium called endothelium. The middle layer is the tunica media, and it consists primarily of smooth muscle and elastic fibers. The outermost layer is the tunica adventitia or tunica externa, and in this layer you have collagen fibers. Hemostasis involves the stoppage of blood loss. There are three phases in hemostasis. We'll look at each phase in more detail, but I want to first of all just list them for you. Vascular spasms, platelet plug formation, and coagulation. Let's start with vascular spasms. Vascular refers to blood vessels, and spasms refer to muscle contraction. Smooth muscles in the tunica media contract. This helps decrease blood loss. This is called vasoconstriction. There are three stimuli that will bring about muscle contraction. Local pain reflexes. This involves the autonomic nervous system. Two chemicals released by activated platelets, thromboxane A2 and serotonin, as well as the chemical released by the endothelium when it is damaged, endothelin. The second phase is platelet plug formation. This involves platelet adhesion. This is the platelet binding to the exposed collagen fibers, and platelet activation, the release of chemicals from the platelets. When the endothelium is damaged, the underlying collagen fibers are exposed. Platelets become sticky once they are exposed to these collagen fibers or come in contact with them. What this means is that platelets begin to send out spike-like processes. Damaged endothelial cells will release a protein called von Willebrand factor, or VWF. This protein will bind to the exposed collagen fibers. Platelets will have receptors for the VWF. Therefore, the von Willebrand factor helps bind the collagen fibers to the platelets. Once the platelets do this, they become activated and undergo degranulation. What this means is that they release chemicals that are stored within granules. These chemicals include ADP, adenosine diphosphate. This should look familiar to you. Recall that ADP plus phosphate makes ATP. Thromboxane A2 and serotonin. Recall from the previous slide that thromboxane A2 and serotonin bring about vasoconstriction. These three chemicals will attract other platelets to the area. This is the aggregation. This type of feedback mechanism is a positive feedback mechanism. As other platelets come to the area and bind, they are activated, releasing more chemicals which will attract additional platelets, and this will continue, forming a platelet plug. This prevents blood loss. Aspirin inhibits thromboxane A2. For this reason, individuals that have coronary heart disease may take a daily baby aspirin to prevent blood clotting. In this illustration, we can see the platelet plug formation occurring. So if you begin at the left with number 1, the platelets are going to adhere and are activated by the exposed collagen at the site of vessel injury. Remember that in order for the platelets to bind to the collagen, they will need the von Willebrand factor released by the endothelial cells. Activated platelets in number 2 will release ADP, thromboxane A2, as well as serotonin. Remember that ADP, thromboxane A2, and serotonin will attract other platelets to the area. Thromboxane A2 and serotonin also will bring about vasoconstriction. Other platelets come to the area, bind, and are activated, and this creates a positive feedback mechanism. A platelet plug is produced. For number 5, notice the green arrow with the prostacyclin and nitric oxide. Normal, healthy endothelium is smooth, and it releases the prostacyclin and the nitric oxide, and this will inhibit platelet aggregation. So a platelet plug is contained or confined to the site of injury. Let's move on to the third phase, coagulation. This is a little bit more complicated. Before we look at coagulation, try to think of what a stationary blood clot is called. It is a thrombus. If it begins to move, it is an embolus. Coagulation involves 13 clotting factors. Most of these will be proteins synthesized by the liver. Vitamin K, calcium, and the clotting factors, as well as platelets, are required for coagulation. Vitamin K is necessary to synthesize 4 of the clotting factors: 2, 7, 9, and 10. Calcium functions as one of the clotting factors, and platelets will be releasing chemicals involved in coagulation. Warfarin or Coumadin inhibits vitamin K's action. That is why warfarin can be taken to prevent blood clotting. It will inhibit the synthesis of 4 of the clotting factors. There are 3 pathways in coagulation. These pathways function as enzymatic cascades. What this means is that the first protein is activated, meaning it will change its shape, and when it becomes the active protein, it will function as an enzyme for the next reaction to convert an inactive protein into the active protein, which will then function as an enzyme for the following reaction. In this way, it is a cascade. The 3 pathways include the intrinsic pathway, and we'll look at each one of these in greater detail, the extrinsic pathway, and the common pathway. So let's start with the intrinsic pathway. The term intrinsic means within the organ, and here we're talking about blood vessels. So what occurs here is that the first clotting factor in the cascade is activated within the blood vessel. Activation can be the result of coming in contact with collagen fibers, the exposed collagen fibers. In the extrinsic pathway, the activation of the first clotting factor occurs in the tissue. So outside of the blood vessel, this is going to require tissue factor, which is clotting factor number 3, released by damaged tissues. So blood has left the blood vessel. Typically what happens is that both the intrinsic and the extrinsic pathways will occur at the same time. Both pathways are going to end with a chemical called prothrombin activator. The common pathway involves converting prothrombin into thrombin, which then will convert fibrinogen into fibrin. And we'll look at all of these steps. This figure 17.14 is in your textbook. You'll see that the intrinsic pathway is on the left and the extrinsic is on the right. Both pathways end in the prothrombin activator. So we're going to start with the intrinsic pathway. So recall that the first clotting factor, in this case it's number 12, is activated within the blood vessel when it comes in contact with, let's say, collagen fibers, exposed collagen fibers. Notice that in this pathway you have 12, which is converted into 12 subscript A. So all that is showing you is that 12 is a protein in the inactive form. When it's converted into 12A, that is the active form. And that protein then will function as an enzyme for the next step. Notice that 11 is converted into the active 11. And this continues here. Platelets also are involved. You can see that on the left there, where 9 is being activated, or the active form of 9 is combining with the active form of 8 to produce a complex, and then that will continue on down, where you have 10 being activated, which will then activate 5. Calcium is required here as in an earlier step, and also all of this with the phospholipid surface forms the prothrombin activator. Let's look at the extrinsic pathway. Notice calcium is required as well as and tissue factor, which is clotting factor number 3. So notice that the tissue factor is going to activate 7, and the tissue factor and the active 7 will then be used to activate 10. Don't worry about learning all of these numbers, but what I do want you to know is that calcium is involved in each one of these steps or pathways. Platelets are also involved, and these are activated platelets. Try to figure out which pathway is going to take longer. It will be the intrinsic pathway because there are more steps involved. Know where the activation occurs for each one of these pathways and what activates the first clotting factor, and then what they both lead to, the prothrombin activator. Again, you don't need to know the individual numbers, just the general information that I mentioned here. Now let's look at the common pathway. In the common pathway, prothrombin is converted into the active thrombin, and thrombin is required to convert fibrinogen, which is a soluble protein, into fibrin, which is an insoluble polymer. Fibrin is going to bind to platelets. Platelets have a receptor for fibrin, and this helps connect the platelets to one another. Notice in this step you also have calcium as well as an active clotting factor number 13. So in the presence of calcium in the active number 13, the fibrin insoluble polymer cross-link to produce a fibrin mesh. And this is what you end up with during coagulation. And this mesh helps trap the red blood cells and prevent blood from leaving. Anticoagulants are chemicals that will prevent coagulation or inhibit it. Warfarin is one such chemical. So you need to go back and try to figure out how it functions as an anticoagulant. I'll ask you when we get together as a class. There are two types of hemostasis, primary and secondary. Primary hemostasis involves the first two phases, vascular spasm and the platelet plug formation, and secondary hemostasis involves coagulation, the last phase. In small blood vessels with minor breaks, you might only have primary hemostasis, but in larger vessels, you would go to secondary hemostasis to try to stop the loss of blood. This enhanced photograph is of a fibrin mesh, and then you have the red blood cells. Finally, let's look at clot retraction, vessel wall repair, and fibrinolysis. So we'll start with clot retraction. Platelets have two contractile proteins. Those are myosin and actin. These should sound familiar to you from muscle. Remember, during muscle contraction, you have actin and myosin proteins that are going to be involved in the shortening of the muscle fiber. So the actin and the myosin contract. This pulls the platelets closer to one another, pulls the two ends of the damaged blood vessel closer together, and helps tighten the platelet plug, making it more condensed. Vessel wall repair will then occur, and this is going to involve two chemicals. Platelet-derived growth factor, and this factor is going to stimulate smooth muscles to begin to divide, grow and divide, as well as the fibroblast. So what you're doing is you're replacing the cells that were killed within the blood vessel. Remember that the fibroblasts are cells that give rise to connective tissue and the proteins there. In addition, vascular endothelial growth factor released by a variety of cells will cause the endothelium to reproduce, and endothelium is simple squamous epithelium, so that the endothelium can be replaced. Once the repair has occurred, you then have to break up the blood clot, and that's fibrinolysis. So lysis just means to break apart. You're breaking apart the fibrin. Remember, the fibrin is what's holding the platelets together. This is going to involve plasminogen, which is an inactive protein that will be converted into plasmin, the active form. So plasmin is going to be the enzyme that breaks down the fibrin. Plasminogen is activated into plasmin by thrombin and tissue plasminogen activator.